good afternoon, and I'm glad so many people are interested in Valhalla. So I'm going to put that code for asking questions on every single slide, so whenever you're ready for your first question, you can snap it. You can also download the code for this presentation. You can get the slides for the presentation. You can see the URL here. And sorry. So just a couple of words about myself. So I'm Cay Horstmann. I've been writing books. The book that most people know me about is this thing called Core Java that is now in its 13th edition. And there'll be a 14th edition later this year covering Java 25. And yeah, I'm a Java champion, and here you can find out more information, whatever. So, you know all about these OpenJDK projects. There's a project Amber for that does things like the pattern matching and other productivity enhancements, records, and so on. There's a project Loom. I'll be talking about Loom actually right after this talk, also in kind of the same more in-depth way. So show up for that. There's a project Panama for foreign functions so pretty soon you can do all of your AI work right in Java when it links to the C++ libraries through Panama. There's a thing called Leiden to improve startup time. And there is Valhalla, val for values that gives us value types. So that's where we're at. So why do we care? So ever since Java 1.0, 30 years ago, or almost 30 years ago, we've had 8 primitive types, and everything else is a reference type. And they're completely different from each other in so many ways. So primitive types are flat, meaning they're stored right there. If you have an int, it's stored as an int. There's no indirection. And they're also dense. If you there's only the int. Whereas if you have an object, the object has it's somewhere on the heap. There's a header that describes what the object is and all of that. So none of that is present for those primitive types. Equal compares primitives by value, whereas it compares references by their memory address. Primitives, of course, can't be null because there's no indirection. So, and that's probably good, right? You don't have to initialize a primitive if it's a field. It automatically gets initialized as the all 0-bit pattern, which is either the number 0 or 0, or it's false for a Boolean. Maybe lesser known fact, if you have a long or a double on a 32-bit VM, they can tear. That means that an assignment of one double to another could in theory be interrupted when your current thread loses control, and only half of it is assigned at that point, and another thread could observe that torn value. We'll talk about more of that later. These 3 exclamation marks here are just markers for me and for you to see that those are things that we're going to be digging into in a little while. So why do we care to expand the realm of primitives? Well, there are other kind of values that you would like to be able to treat as primitives, because think of like currency values or measures, or date and time values. When you have those, they're really kind of like glorified numbers, and it would be nice if they could be efficient. But you don't really want them to be just numbers because you want to be able to invoke methods on them. So you want something that, as Brian Götz says, that codes like a class but acts like an int. Sure you do, right? And obviously for performance reasons. There's a reason the primitive types are not objects, and that is performance. You save a lot of memory. You have better locality. Now imagine you have an array of 1 million somethings, and if they're objects, then each object is somewhere separately on the heap. When you now have to step through all of those values, then they need to be fetched from all sorts of different memory regions, and so it'll put pressure on your hardware cache, and your program will probably perform poorly due to cache misses. But if you have it all in one contiguous array, then you're going to have less of that risk. And also, of course, if you have objects, the objects get garbage collected. That's work on the garbage collector. If you don't have objects because everything is put straight into an array, then there's no pressure on the GC. There's another reason for just for programmers, and that is right now we have this nasty situation with the wrappers that you have int as the basic type and you have integer as the wrapper, and so I've picked this thing at random. You can make a function from integer to Boolean, and that's different from a predicate of integer, and it's different from an int function of Boolean or an int predicate. So you have 4 different types for what really should all be the same thing, and that's what these wrappers get you to. When the wrappers were first invented in Java 1.5, that was before anyone was really thinking about doing functional programming in Java, and it wasn't that big a deal. But then once streams came in Java 8, and we were doing a lot more, and in lambdas, of course, and we started doing functional programming in earnest, it became a real pain. So we do care for these 2 reasons. One is efficiency, and the other is that we want to clean up the programming model so that one can erase the distinction between classes and primitives. So it starts out super simple. Fairly soon, we're going to be given a new keyword, value, and you can declare a class as a value class. And a value class is in all ways exactly the same as any other class, except it gives up identity. That means that if you have 2 objects of a value class, they're getting compared not by their reference, because they may not have a reference. They're just values. So the comparison is done by value. The fields are compared in turn. Also, the hash code that only depends on the value. There are no synchronized methods, because a synchronized method would mean that you have an object, and somewhere in the object there's a field for the magic lock, and there is no objects. Right now you cannot synchronize on an int, and so you cannot synchronize on any value. And that's all you do as the programmer. You say, I want this to be a value. And that gives the VM a powerful hint, namely that these things can be freely moved about. They don't have to be on the heap at all. And the VM may, if it feels like it and it's having a good day, then it may do whatever it wants to do to improve performance. You as the programmer will not have the fine-grained control to tell the VM exactly how that should be achieved. You give it this hint and say it's a value. We'll see a couple more hints as this progresses, but this is the first and most important one. Now, many value classes will probably be records. So here I have I have a record point. A point has an x and a y coordinate, and it has a method just to show that it can be done. And I'm declaring it as a value record as opposed to a regular record. And that means the semantics is completely unchanged. They work exactly like the point record, but we've now given that hint to the virtual machine that these things could be flattened. So there is a JEP out there, JEP 401, that has all the details, but really there aren't that many more details. There's a couple of rules. Well, actually, some of you might have gone to Falk's presentation that preceded this one, and he's gone over some of those rules with you. But there really is not that much to it from the point of view of the programmer, so we're kind of done and we can go and have our coffee break. No, I mean, the reason I'm giving this talk is to show you how you can now watch under the hood that something interesting is actually happening. So surface syntax semantics is almost zero, but there's a lot of stuff going under the hood. So a bit of terminology. So when I talk about a value, then so far we've had 2 kinds of values. We had a primitive, like here the number 42, or here a reference. That's the value. And now we have this new kind of value. There's these value objects. Like here I have a value object of type point. And you can see these values here, they can live on the heap. This thing is supposed to be the heap. Sorry, it's the stack, or in registers. So this thing here, they're just values. They can be moved around in any way. Or they can also live inside objects. So here I'm having some other object. You can see it's an object, it has a header, but inside it I wanted to have this point value. That's what my diagram here is supposed to show. So values can live in registers, in the stack, or inside other objects, and of course also inside arrays. Oh, by the way, I felt a little bad. You all pay big money for this conference that I have this hand-drawn diagram, and I didn't have the time to make it nice, so I asked ChatGPT and say, can you clean it up? And so I guess I'm sticking with those hand-drawn diagrams for a little longer. All right. So how can you try this stuff out today? So my message to you is that you can actually try out all of this today, and I'm giving you detailed instructions, some of which I will be able to demo in real time, but we only have 45 minutes, including Q&A, so I'm going to skip some of the demos. But you can do this all yourself. This is everything that I'm showing you is working today. So if you just want to mess around and make a value class, you can you could download a build, but that build is almost always outdated. It's not really worth it. There's a slightly more modern one that Mark Hoffman keeps at this URL. But if you really want to experiment in earnest, you should build your own, and it's not that hard. On Linux, it's particularly easy, and so you could do this in a Linux VM and experiment with it. You just need to clone the repo. There's a few missing packages. You say, how do I know that they're missing? Because you just try to compile. And you just run bash configure, and it'll tell you. And after 3 or 4 tries, you have all the missing packages installed. And then you make it, and then it puts the build somewhere. And if you use SDKman, who of you is using SDKman? Okay, so most of you, that's great. If not, you should definitely look it up and then also raise your hand next time. You can tell SDKman to make a custom VM and give it a name here, call it Valhalla, and I give it the path to where I have it installed, and then you can use it to switch to Valhalla at any time, as of course you will want to do from now on often. So then when you run it, you will see that this value class syntax is supported today. Of course, as preview, so you have to put enable preview everywhere. I tend to forget that. And so let's just try something that's really easy. What do you do with points? Well, the first thing that came to my mind was Brownian motion. Brownian motion means if you have like a particle inside a liquid, then the atoms of the liquid push it along, and then it moves. And so the here I'm now taking my point, and I'm moving it by a random x and y that are between -0.5 and 0.5. And then I do that a million times, and then I try to find out by how much did it move. It turns out it's a law, it's a thing in physics that it does, on average, move by something. You can predict how much it moves. Even though you would think in theory all these plus and minus values would cancel each other out, but in fact, statistically, they don't. So that's what we're going to do. And so after here, I have 100 million iterations. You can see this particle has moved some amount of time, and we can see what the timing is. So I timed it with Valhalla, and it moved by that took 7 seconds. And I did it without Valhalla, and that was 8 seconds. So that was not so amazing. Okay, well, you have to start somewhere. So, but even with this simple program, and so the only difference in the program, if I just really quickly show you the source, is what happened to my carefully arranged source display? Let me see if I have it in my other presentation. Nope, it's just one. Okay, sorry about that. Get it. Huh? So we are in with Valhalla point. So ignore these things. They'll come up in a minute. They're commented out anyway. Here you see the keyword value. That's the only thing I'm doing. Okay, otherwise, there's nothing interesting going on. Now I'm running this code. You've seen it's minutely faster. But to see something more interesting, we're going to look at how these objects were actually allocated. Now, without Valhalla, you would expect that you would, for each of the, when we look at the code here, let's see what happens. Each of the calls to move by actually generated a new point. That's important to see how this code was set up. So I'm really generating 100 million points here. Because I'm going through the loop, I'm calling new 100 million times, so I get all these objects. Now, if they are living on the heap, we can figure out how big they are. The true doubles take 16 bytes. There's a header of 12 bytes. They need to get padded on boundary. So there actually is a 32 byte per point on the heap. And so if I have 100 million of them, it's about 3 gigabytes. And to see that, we can run this, and I'm not going to do this now because it just takes time, but you can easily do this at home. You can run it with this magic flight recorder flag and make a flight recording. It puts it into a file name, and then you can look at the flight recording with a Java mission control. So it's a good exercise to do it if you've never done this before. Where is my Java mission control? Run it again. And so if we look at the memory here, and so what do we see here? First of all, we see 3 gigabytes of objects, and what you can see here is you can see how the garbage collection kept on happening, because these objects are super short-lived. So the garbage collector really did collect 3 gigabytes of objects that were previously generated. That was without Valhalla. Now let's look at it with Valhalla. And if we look at the memory. Okay, you see nothing. Okay, none of these objects were ever generated. Now, the virtual machine took the opportunity to say, these things are short-lived, they have values, no one told me to put them into an object, and so it didn't do it. And so that is kind of a super win already, right? So 24 mega. Right, no GC activity whatsoever. So at this point, you should be impressed. Right? So this is something you can do with this code that you can try out today, and it actually works. It only took 11 years to get to this point. All right, more. So now we want to find out why isn't Valhalla faster? Remember, it was just a teensy amount faster. And so to do that, you can look at the generated code. And you need a different tool for that. You need this thing called JITwatch, and here I'm giving you instruction on how to do it. And so I already loaded up JITwatch here. Where is it? And so so I generated a log, and you can see here the instructions on what you need to do to generate the log. I'm now going to open the log, and if I open the log with Valhalla, then I need to click on Start here. That's bad. I know what happened. Okay, now unfortunately it's smaller because I've forgotten how to do this scaling thing. We'll live with it. No Valhalla. Start. Okay, and now you see here the no Valhalla thing. The reason you didn't see it before is that I have to run JITwatch also with Valhalla so that it can read the class files, because otherwise it cannot read the more modern versions of the class file. And so now if I look at the main method, I will be able to, come on. Oh, it's already here. Thank you. Yes. I will be able to look at the generated bytecodes. Unfortunately, the display here is a little bit weird. And there's a reason for it. and if you look carefully here, you will see that it throws an exception because it's not yet used to Valhalla, and I'll actually come back to that exception in a minute. And so I have to mess a little bit here with the UI, and I'm just going to uncomment the source here. So the thing that I wanted to show is that we all read bytecodes like palm of our hand, of course. So I want to look at the move by method here. And so actually move by, if you carefully look at the bytecodes, you will see that move by is not actually, once it's sufficiently JITted, does not actually happen, but instead it has two assembly instructions to just move the register values. And so if you compare, oh, this is no Valhalla. No, here it does call it. So let's do it with Valhalla. I don't want that. Open log with Valhalla. Do the same thing. Start. And we have with Valhalla. Brownian. The demo gods are not on my side today. Oh, no, I mean, because I'm stupid. Okay. Unclick the source. Go to random. Go to the move method. So yes, so now previously you did see the call, and here you will not see the call because the method is never called, everything is inlined, and that's fine. So why is it still slow? If you keep on following the bytecodes, you will notice that what is actually done is not only has it inlined this method, it has also inlined the calls to Java to random. And so here we've been calling math.random, and it actually inlined the calls to math.random. And if you follow along the bytecodes, you will find that the work that's involved in calling math.random is so much more than what was involved in doing that one, in the object allocation, that completely messed up your benchmark. That's actually a danger whenever you make a benchmark, you call math.random, that it's just a surprisingly expensive method. So just a bit of background on this here. What do these bytecodes even mean? And what do the assembly instructions even mean? So you know, of course, that Java-C generates bytecodes, and that then the Java interprets those bytecodes. But of course, what it really does is it doesn't interpret them for very long. If a method is called more than a few times, then they get translated into machine code. There's two levels of compilation. There's what's called a C1 compiler that is there for fast startup, and then there's a C2 compiler that's there for longer running programs to optimize the hell out of them. And it's very, very good at it. It checks which methods are called often, it focuses its attention on those, and then they get compiled. And also loops that are executed a lot do get compiled. Methods can be inlined, loops can be unrolled, meaning that rather than calling the loop n times, maybe you call it like n over 16 times, and you then have 16 copies of what goes on inside the loop. So Hotspot will do all of those things. And so in our case, Valhalla inlined the call to move by, but it also inlined random, and that it doesn't matter whether it inlines it or not, but you can really see by counting the assembly instructions that random is kind of expensive. So that means that these naive benchmarks, they're always bound to fail, and so whenever you want to make a good benchmark, then you want to use like a micro benchmarking tool, of which there exists only one that's any good, I think, and that's JMH. So that's kind of a skill set that's good to have, that I wish I had myself. But it's so I always steal some benchmarks and then I try to build on them. So I'm giving you these instructions here that you could use if you wanted to do that, and it's definitely, again, a worthwhile thing to know. So I did my next benchmark, and here's what I did. I said, well, this thing with the random numbers that's unpredictable, I'll just use some other way of messing up these points. I want to mess them up 100 million times. Random was too expensive, so I'll just mess them up in this way where I'm scrambling the x and the y, and I'm doing some adding and some subtracting, and thereby surely I'll get a cloud of points, and it doesn't really much matter what they do, because I just want to prove that it is a time saver to do them as values instead of as objects. So I did this 10 million times here, and fantastic. Look at this. Right? So I've gotten the time down to essentially 0. Well, Valhalla is good, but can be that good? And so what happened is that with Valhalla, the inline call to transform caused this loop to be unrolled, and hotspot, I think it just did the thing that says I'll unroll it 16 times, and it realized, which I didn't realize, that by sheer dumb luck, when you call transform 4 times in a row, it did exactly nothing. So the switching around and pluses and minuses, without my knowing that they, yeah. And so as an exercise, you can do this. And you can actually see the code that that hotspot generates is nothing. It has optimized the entire thing away. So one remedy would, of course, be to have a better transform, right? I could, instead of just using 1/2, I could use whatever, pi or something, and then do a more interesting transform. But really, the better way is just pre-compute the random numbers. And so you can download the source code and see how it's done. It's nothing deep. And so when you do that, then it turns out that now you get a perfectly solid result where you get about a 50% improvement in speed with Valhalla. So that's nice, right? And it's also, it makes sense. That's within reason of what you would expect for this kind of situation. You're doing almost nothing, but in one level you have to do it with objects, and the other level you do it without objects, just by moving numbers around in registers. And so that's the kind of performance that you would expect. That's also probably, a kind of a best case scenario here. And remember, the much less memory consumption. So clearly this is something that you want to have, right? At this point, for any kinds of, if you have lots of smallish objects, then you want that. So moving on, now I want to have this array of many points. Before I didn't put them in an array. Now I do want to put them in an array, and there's a teensy problem with that. And that is, value types can be null. So if I have a point, then it's an object. I only put value before value class, but it did not change the semantics of the class at all. So I can still have nulls, and that kind of now makes it a little difficult. Now I have a variable here on the stack, and it could be null, it could not be null. Well, how is the memory layout then going to work? Previously I said, oh, I can just put the x and y right on the stack. I don't need an object. But now, how do I distinguish a point from the null? There needs to be an extra bit somewhere. And that's particularly painful in an array. You have an array of whatever, a million points. So it somewhere needs to also now find a million bits so that it can see which of those are occupied versus not occupied. And that's something we would like to be able to say, we don't want that. Now, even today, in many situations, the JIT will be able, for local variables, to reason that they can't be null, and therefore it doesn't actually have to allocate an object. But as soon as they are inside fields, then it can no longer do that. And also when they come in as parameters, it can't often do that. So it has a limited view right now that allows it to do that kind of optimization. And so what we need is some way of telling the VM, I actually will never use the null for this. And so the syntax that might change, but I'm pretty sure it's fixed, is that you put an exclamation mark or a bang behind it. So point bang means this it's never going to be a null. And the compiler will enforce that. So if you try to put in a null, then it'll say, well, that obviously doesn't work. And also, since you can defeat the compile checking by going through object, the runtime will enforce that. So here I have an array of non-null points. And if I later try to sneakily put a null in there in a way that the compiler cannot detect that, then the runtime system will throw a null pointer exception. That's really no different from how arrays already work, because you can already, by casting to object, you can put, if you have an array of points, you could put in an object of a different class, like a watermelon, and then the runtime system will give you an array store exception. So arrays are already instrumented to detect whether you put in the wrong thing, and it's not a big thing to do them like this. So, by the way, this will come to all types, not just value types, and there's a JEP for it sometime soon. Now, the second exclamation mark that I had is that primitives are initialized with 0 bits, but that's not always good for objects. Like a local date that's initialized with all 0 bits is probably not so great, right? As a default, if you have an array of whatever, 1,000 local dates, do you really want them all to be January 1st, 1970? It's not clear. So, and for if it's in an array, it's a problem. For a local variable, of course, it's not a problem, because local variables are always explicitly initialized. The issue really comes with fields and arrays. And so for oops. Well, thank you. So what are you going to do for an array? You really have to come up with a value for every field, and that's so there's two issues. I shouldn't have jumped ahead to arrays. For instance field, this will be solved by a new notion of what's called strict initialization. So a strictly initialized field is one where the compiler can see that it was always under any circumstances initialized. And there's a bit of a technical rigging going on right now, where now you are able to initialize some variables before the call to super, and I'm not going to go into the technical details. But the concept is that the compiler will make sure that there always is an initial value. For arrays, that's a little bit nastier, because you have to actually give an initial value. So when you make a new array here of string bangs, then you could maybe give the actual strings. If there's a small number of them, then it can check. Or you have to give like the thing to put in for each of the values if there's only one. Or you might have a lambda to initialize each with a particular value. The syntax here is still up to debate, but it'll look somewhat like that. So, but the point is that when you have a something bang, it must be initialized for sure. And that way, when the question never arises, should it be initialized with a 0-bit pattern? Because the 0-bit pattern it makes sense for points maybe, but it doesn't make sense for other things. And there was a long discussion about this. It took several years for them to arrive at this. So the idea is that the default 0 bits shall never be observed. Yeah, let me just leave it there. Now, this is something that we would like to try, and unfortunately, we can't quite try that. So the current Valhalla build does not yet support the bang syntax, and so one has to use some annotations. Instead of using a bang, you have to use the null restricted annotation, and you also have to use strict to say that this thing will be strict because it's not quite in the current build as something that it can compute. And there's we'll come to another annotation a little bit later. Also, to initialize an array, that syntax with the braces and the default is not yet supported. You actually have to call a method to do that. And you have to, because these are all internal things, you have to put in flags. And so I'll just show you what the code actually looks like. Where we have it. Yeah, so what I'm going to have to do here is I'm going to have to comment these things out. And in this thing points here, you can see I'm going to make an array of 100 million points. And I have to, instead of saying new array, I have to call this thing to say, give me this array, and this is the default value to be used. Of course, it doesn't call the constructor 100 million times. This is just a value. It just uses that value to slot it in there. So it is not quite as fast as just blasting a 0 in there. It still has to fill in that value, but it's still there is instructions to do that fast. So, and if you want to observe that, and we won't have time to do it in a real demo, but you just have to take it on faith. It's actually pretty easy to do. You just run this program, and then you call sleep, and then you use a JCON and ask for a class histogram. And when you do that, you're going to find that there is in fact an array that's this long, and when you compute the lengths, you'll find out that means it just has doubles in there. So there's 200 million doubles sitting one after another. Double, 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 double. No indirection, no nothing. If, on the other hand, you take off here this annotation, there's a loosely consistent value, it will not do that. It'll use indirection. So that's the last piece of the puzzle that I have to explain to you. Where that part comes from, and that has to do with tearing. So as I said before, long and double may tear, and that meaning that a thread may write half of it. It doesn't really happen on 64-bit VMs, but now if you have a point which is 2 doubles on a 64-bit VM, that is definitely a possibility. So here I have a picture where I'm moving a point. I'm having 2 threads that each move a point into some target, and it could perfectly well happen that the first one gets interrupted as it has moved the x but not yet the y. Then the second one moves both the x and the y, and then the first one gains control again and overwrites the y. And can you see this? Absolutely. So I have a little demo program that does exactly what I've just told you. It simply has 2 threads that busily move points into a common target, and I've cleverly made it so that each of those points has the x and y coordinate the same, so you can tell where the tearing happens, because tearing would happen once you observe a value that has the x and y values different from each other, and in that case it'll print out the offending point. Here you see one that you see a few where x and y are different. It doesn't happen a lot, but it does happen a few times a second. So it's a definite real thing to observe. And so why would you ever want to consent to such madness? Well, you're using doubles, so you're not totally unfamiliar with the phenomenon. It's just a question of efficiency. For some values, you might say, I don't care. And in that case, one would then have to annotate them as such. Right now, it's an actual annotation. It will at some point become either a marker interface or a keyword. We're not totally sure. Now, if variables, if values are allowed to tear, then the current implementation of Hotspot will happily pack them into a flat array. If you're not happy with that, then right now it says, oh, it's too complicated for me to try to lock on each of the objects. Then it'll just fall back to the old implementation of using pointers into the heap. So you really have to say both the null restricted and the willingness to tear if you want to observe that sweet array of 200 million doubles. So that's kind of where the thing is at right now. Together with a blueprint for you to see with your own eyes that this is actually working and not just something that Brian says, yeah, trust me. So they've come a long way. And here's what we're going to be getting when this package is complete. We're going to get the value modifier. We're going to get the bang syntax in all likelihood. We're going to get some way of indicating, yeah, I'm fine if this particular type tears. And many of the standard library classes that are already marked as value classes will become actual value classes. Those are the wrapper types, integer, double, and so on. Optional For example, right, I mean, optional is right now kind of irritating that you have yet another level of indirection for optionals. So that'll be gone. The various time classes. And that's pretty much all you're going to get. That is Valhalla. Everything else of Valhalla is under the hood. So that's why what I wanted to show you today is how you can actually, with the tools that you may be familiar with or that are easy enough to find out how to use them, how you can observe with your own eyes how to do that. So let me see how we're doing on questions. Okay, there's a bunch of questions. So in that case here, let me quickly go to the end here. Yeah, and so what's remarkable about this, they've been laboring on this for over 10 years, and there's so many different things that they have tried. And really kind of the key observation was at one point to say, we're just not going to go down this rabbit hole or that rabbit hole, but keep it simple. And so now we have a feature set that actually is comprehensible. But the next can of worms is already there. This all stuff at some point will have to work with generics, and I'm not going to get into that today. All right, so this will happen. Some workloads will see really significant performance improvements if you have lots of small values, and surprisingly many programs do. Then they would simply not be on the heap, and thereby your garbage collector will have less garbage to collect, and there'll be some improvement in running time. The primitive types will almost go away. An int will essentially be the same thing as an integer bang. There's some minor technical differences, and that's good because you always want to have some question to ask on those recruitment interviews. Yeah, there's rules for conversion and overloading and all of that, and they'll get even more complex, but none of us understands those rules anyway, so it'll be fine. Generics, that's going to be, I mean, the ultimate, the real dream of Valhalla is, of course, if you make a list of lowercase int, which is now a list of integer bang, that it'll be backed, like an array list will be backed by an array of int, right? No wrappers, no nothing. And it will come eventually, but it's a hard problem. So when those come, benchmark to see if they're there for you. And so I've taught you on how to do some of that benchmarking. So now I've never done this before. Let's see if these questions here are showing up here. Can values contain object classes? Absolutely. And then they will contain a reference. Unless they themselves are value objects, and then they will be nested inside. So you could imagine a class circle that has a value class circle that has a value class point instance in it, and then it'll be x, y, and radius, right? All next to each other. So you use profilers for performance tuning and debugging. How will I check whether the JVM is using stack or heap on value objects? The JVM can do what the JVM wants to do on a case-by-case basis. So it could, in some parts of your program, move the things around just in registers, and elsewhere it could store them on the heap, depending on how often this thing happens and how it wants to work on the optimization. And really, the profilers will not really tell, they might tell you, how fast something is, but they're not necessarily going to tell you exactly what the VM does. If you want to see what the VM does, you need to generate the JIT tracing and then look it up in something like JITwatch. It is doable. There's a lot of instructions, but you do at some point get better at staring at those assembly instructions and figuring your way around them. And now at some point you might of course say, now why do I really care? I mean, I cared for this talk to really show you that something interesting and exciting is happening. In practice you will probably just profile and say, well, that's nice, and not figure out exactly how the JIT does it. So can a point question mark be cast to a point wow or a point bang? And yeah, you can cast it, and the cast will fail at runtime if in fact there was a null, just like any other cast. Can I pass a reference with unknown nullability? Well, if the unknown nullability, then that's where we are today. It's not clear whether we'll ever get a point question mark syntax in Java. It'll probably be the case that point is what in Kotlin would be point question mark. Can let's see, do we have this? Is the at string bang array and the new string bang, is the second bang really needed? Yes. It does. I mean, because otherwise it's going to say, well, on the right-hand side there is an array that might contain nulls, and it's just not the same thing. So it will be a compile time error. Could you cast it? Yeah, you could cast it. I don't know what would happen if you cast it when the misdeed would be detected. One thing that I forgot to mention is that the bytecodes, there's no new bytecodes. So the bytecodes are all the same, and when they get compiled down, the compilation into machine codes will change its behavior depending on whether it had a bang or whether it didn't. Does that mean that value classes are similar to structs? They're similar, but if you have a struct, then you know that the struct will be flattened. Whereas with the value class, the VM may, if it feels like it, flatten it, or it may not. And in fact, when the VM first starts, it probably will not do it at all. And as the code warms up, it may do it. No, so it doesn't matter whether math random is inlined or not. It is slow. It simply is that it's slow. Why did they inline it? Well, I guess because you get a bit of better locality when you do that. Can value classes have non-value classes as their field? Absolutely. And then they simply store a reference. And what does that mean for comparison? It means that the references are compared with equal equals. Yes, now this is a very good question. Sometimes, like with points, sometimes you might say, I'm fine if they tear. And otherwise you would say, well, that would be terrible. Sorry about the pun. And why do you have to fix that in the type? And I'm very sympathetic to that criticism. And it has been discussed. And right now the feeling is that it's such a complicated point. We don't want programmers to have to think about it every time they use one of these things. It's kind of like right now, double. Do you say I want a non-terrible double versus a terrible double? Right now you just have double, and so that was the feeling. But it is not perfect. Can you call a method on an int? Yes. So a string bang is not the same thing as a string double while. Oh no, that's just a question. Well, no, it's a different type, right? A type is a set of values, and this has one value less. What will happen when you call getClass? On a record variable, you will get the class. I mean, whether it's a value record or a record, you'll just get the class. If the value class loses identity, can we not do instance of? You can do instance of right now on floats, right? So I have to think what the semantics. The semantics are going to be kind of trivial. How can tearing appear if value objects are immutable? Well, a double is immutable, right? I mean, 3.14 is always 3.14, but yet when you move it from one place to another on a 32-bit VM, you could move the first 32 bits and then get interrupted, and then in the meantime it gets overwritten, and later you move the other one. So it has nothing to do with immutability. It has to do with the fact that if you have a large pattern of bits and you move it from here to there, that process is not by default thread safe. Or it is actually by default thread safe, but if you allow for tearing, then it's not. So what are the benefits of value classes from marking them with the please don't tear option? Well, at some point, you could imagine that there is a smarter way of checking for assignment than putting. You could, for example, put a lock around each assignment. And there might be some lightweight way of doing that locking that we could discover. So this it's going to be shifting how good the VM is at something. Like today, as we observed, this particular VM was unwilling to give me a flat array for the default non-tearable ones. But I think that's going to change, because otherwise it would erase a common, and so we want to be able to have that use case. What is system identity hash code? You will not be it'll be an exception. You will not be able to call identity hash code on a value. So it could be. I don't think the compiler can catch it, because it'll turn value into an object, but it'll be a runtime error. So I think that got me to the end of it, and we're certainly out of time at this point. So if you have more questions, just grab me on the hallway. Thank you.